Welcome everyone, and welcome to this Tech at Lunch session. Today we will talk about advancing gearbox reliability, vision-assisted conditioning monitoring, which will be presented by Toby Verwimp and Jordi van Malen. During the session, as always, you can ask your question by raising your hand, and we will address your question at the end of the session. Don't hesitate to ask any questions at all. And very important to notice that we are recording this session so we can distribute it at the end of the session. During this week, I will send it to you. Well, then, Jordi, I would like to give the word to you.
Okay, thank you, Miranda. So hello, good afternoon, everyone. I am Jordi van Malen. I am a doctoral student at UGent University, and I will be presenting about vision-assisted condition monitoring for gearbox reliability together with my colleague from KU Leuven, who is also a doctoral student, Toby Verwimp. But yeah, I will be starting off the presentation. So let's get right into it. So a couple questions immediately start this off to pique your interest. Would you be able to visually monitor your gearbox in an R&D environment to really look inside and see what's going on? Or would you like to gain insight into how damage on gears initiates and evolves? Or would you rather have vibration tools that are better than the current versions for your operational gearboxes? Or finally, would you like to make use of the available gear testing infrastructure that will be presented during this presentation? If the answer is yes to any of these questions, well, then vision-assisted condition monitoring might be interesting to you. What is it? It's an automated visual monitoring tool to capture the ground truth, so the real information on gear degradation in situ, and secondly, the improved vibrational based indicators that are developed using this insight using the vision system. Now, what is vision assisted condition monitoring? Well, there's four critical parts to this. First is an automated image acquisition system. So we have a camera that has been fully automated to capture images, and we found some techniques to deal with oil splashes inside gearboxes that would otherwise hinder image quality. Secondly, we also have developed some deep learning tools to analyze these images. This allows us to extract metrics on the evolution of the damage, but secondly, it also gives us insight into how gears degrade. Then we've synchronized this with vibration measurements. This is where the assisted part comes in, to align it with the ground truth, so the real information on how the damage initiates and evolves. And this is then used to develop improved vibrational indicators. And then finally, we've tested this out for multiple accelerated lifetime gear tests. It's been installed on 2 different ones. And we tested out this technique during accelerated lifetime testing. Now to dig a little bit deeper into all of this. So how did we develop it? Well, we have 2 different gear test setups. We have one at the side of UGent, which is an FCG lab gear test setup. This is a very commonly used test setup to do gear testing. This test rig allows to use custom gears to be installed, and then this way you can test out them directly. However, our colleagues at KU Leuven have installed it on an industrial gearbox setup, which uses off-the-shelf gearboxes on which this camera system is installed, and to really try it out how well it works. Now, what can we really now see with such a vision system? Well, in this video, what you'll see is basically the evolution of a single tooth over time. And then I will be highlighting some of the things we can actually notice during this. So the very start, why is it? So as you can see, over time, as the key continues rotating and the test continues, more and more damage is starting to evolve onto the the gear surface. At first, we see a lot of just pitting just below the pitch line that keeps getting worse and worse and worse over time. But then over time, we also start seeing these larger pits appear. Now, this actually means I will go into a little bit later, but this just shows what your system is capable of. We are really able to look at the gear surfaces and see what happens over time. Now, unfortunately, one of the downside is this image is not directly data yet. We still have to do some processing and use some tools to turn this into really data on the damage evolution. And how did we now do this? Well, for that, we have to do a bunch of steps. The most essential first step, of course, is to capture images. Without any images, it's going to be a bit difficult. However, capturing images of a rotating gear is not super simple, as gear moves, meaning that it's continuously in a different position. Therefore, we capture a full burst of images, and then we filter out the ones that are relevant to us, and only keep these, so that we don't have images that do not provide any information, and to avoid redundant images that look the same. Once they've been filtered, we crop them to just the part of the image we would like to look at, being the gear tooth, removing any other noise that could be in the image. And then we start grouping them by tooth, because this is where it becomes really interesting, when you can follow the gears in time. Once they're grouped, we go towards the training of our model. And for the people that have some experience with this, with image segmentation, they know that training these models requires a lot of data, and providing this data is very labor intensive. So we try to find a way to reduce the amount of effort needed from annotators to have a good working model. So what we did here was, for a data set, we selected the tooth with the earliest damage. Then the experts picked out key frames, so the images that we found that looked the most different from each other, and we annotated these. Once they've been annotated, we do a first training of the deep learning model, and we annotate the full data set. Now, at this point, there is still a bit of uncertainty if the model is performing the way we wanted it to. So we start looking at, for example, the evolution of the curves and so on. Do these make sense or not? If these were making no sense at all, we would use what is called active learning, which would select out from the full data set the images that were being annotated in the worst way, so they had the least certainty about the annotations. And we started correcting the annotations by the model, putting them into the training data set, retraining, and we kept doing this until we found that we were satisfied with the results of the deep learning model. Then, once we had a working deep learning model, we annotated the model itself. The model was used to annotate the full data set. And then finally, once the full data set was annotated, we were able to extract metrics. What does this then now look like? What can we now learn from these metrics? Well, I will give you an example of a single test we did, where we annotated the full data set and, for example, some of the things we can see. So what you can see now on the screen is a graph of the evolution of the relative pitted area. So total area relative to the total tooth flank area, and how this evolved over time. And we did this for every single tooth on that gear. What we saw is, at the start, we don't see much. It's a healthy gear, there's no damage yet, or the damage is that small we could not see it with the camera yet. After some time, we started seeing that all the pits started to evolve in the same way, and we had some progressive pitting on below the pitch line, which was just the result of gear meshing, which is to be expected after a certain amount of time. However, something we, for example, noticed in this data set is that, and these are these larger pits I was referring to earlier, we started seeing pits up higher on the gear that were larger, had a different shape, and so on. And after further investigation, we concluded that this was due to wear debris. So some wear debris got caught into the gears, and this caused further pits to develop. And then what we also saw later on is that, this kind of happened again, but even more extreme for a couple of the teeth. And this is just an example of things we can learn from extracting all the metrics from it. I'm not going to go into more details in here and so on. But what's important is that we can extract these metrics And then these metrics can now be used to improve vibrational-based monitoring. And for this, I would like to give the word to my colleague, Toby Verweb.
Thank you, Jordi. So now the idea is to use this direct data that we acquired from the vision system to improve our indirect estimations of the health condition of these gearboxes. And with this indirect data, we mean data that we acquired from accelerometers, torque meters, speed sensors, temperature sensors, and so on. And this we then did for two different test rigs, an industrial gearbox test rig and an FCG test rig. So gears are an example of two gears messing with each other. They result in very specific vibration signatures. And these vibration signatures, both in time domain and frequency domain, they change depending on the health condition of the specific teeth of those gears. And based on these time and frequency domain, or a combination of the two, we can extract features, signal processing-based features, that tell us something about the health condition of those components. Typically, health indicators based on the time domain statistics or on the frequency or order spectrum are used in industry, but we developed indicators, signal processing-based indicators, which are a bit more advanced and rely on the envelope spectrum and wavelet analysis. Besides these signal processing-based indicators, we also developed artificial intelligence-based indicators based on two different architectures. One is based on an autoencoder, another is GAN-based. One specific signal processing indicator I would like to highlight here, this is the wavelet analysis, because besides the overall health condition that we can get from all the other indicators, wavelet-based indicators can also tell us something very specific on in a very short time frame. So eventually for one specific tooth even. And for the artificial-based indicators, we use then the direct data that we acquired using our vision system to give us an idea, okay, when do we switch from a healthy condition to a faulty condition? And this we can use to label our data and then consequently apply semi-supervised learning techniques. But okay, then we have these indicators, but of course we need to evaluate their performance. We do this on 4 different aspects. One of them is early detection, so how early can we detect the defects? The second one is, can we track the fault severity? Thirdly, how robust are these indicators against noise, against different acquisition characteristics, and so on? And finally, is the calculation of these indicators, is it efficient? Can it be used in industry? So if we start with the first one, early detection, this we evaluated by also using information from this vision system. Because by analyzing the images, we know, okay, at this point, we change from a healthy tooth to a damaged tooth. So we know, here shown in red, when we change from healthy condition to damaged condition. And the data in this healthy population, we can then use to calculate a threshold based here on the median absolute deviation. And this threshold we can then use to compare our indicator with that. And then we can apply a moving window, which allows us then to, at one point when we cross the threshold, to detect a fault. The difference here between this fault detection point and the onset, we then quantify as the alarm delay or the detection delay. And this we can do for different indicators, which allows us to compare them with each other for one single data set. But this can also be applied to multiple data sets to strengthen our validation. If we then go to the fault severity, here we see one of the signal processing-based indicators in black over a full test. And we compare it with the pitting area expressed here in pixels for the full gear in red. These two can be compared by calculating a simple correlation. And again, this can be applied for different signal processing or AI-based indicators. And this can be compared to state-of-the-art indicators, where we see that the novel indicators perform overall better than some of these state-of-the-art indicators. This was about fault severity for the full gear, but as mentioned before, we can also see using the camera, we can sort images per tooth, so we can also track the fault severity even per tooth. So here we have an example image of one tooth in the industrial gearbox district, where we have here the annotated flank in blue, and in red we have the pitting. This figure shows for each of the 13 teeth on this gear, what is the evolution of the fault area. And here we see that 3 of the teeth are mostly pitted, more pitted compared to the 10 other ones. So this allows us, using this vision system, to get this information out of our system. We also have, at the same time, our signal processing and AI-based indicators. Here I only show 2 of those. But we can also look per tooth using the wavelet analysis. And then we can have an estimate here in blue of the fault severity per tooth. And we can directly compare it with the image features that we get from the vision system. And then we can see this evolution over a full test or during operation in industrial applications. Where we see that in this region where we have the 3 most pitted teeth, we can see that the signal processing-based, the wavelet-based indicator is correlating quite well with the vision system results. Now, are those indicators robust? This we evaluated by adding different noise levels to our original signals or original vibration data. Here we plotted a state-of-the-art indicator like the kurtosis. It's not performing well. The original signal is not, indicator is not performing well, but even with the extra noise, it's performing worse. While if we follow the same procedure, so we add white noise to the data and we apply again our novel indicator, then we see that the overall progress can still be tracked even with more noise in our signals. This again can be quantified for different indicators across different tests even, and then we can again compare how robust the indicators are against noise in this case. Then finally, we can also compare the computational efficiency of the indicators, which is typically done by running the calculation for a couple of acquisitions, a couple of vibration signals, and then compare how long it takes for a specific PC. These 4 evaluation matrix we can then combine in one single radar plot, which allows us to get an overview of the overall performance of a specific indicator over one dataset. So here we see that the red and the yellow one, the more novel indicators, outperform on almost all levels the state-of-the-art kurtosis. And this we can apply to different datasets on a single test rig, and we can even apply it on more datasets also from other test rigs. This allows us to get an overview of which indicator we should use for early detection. Can we also use the same one for fault severity tracking and so on? But so what can this do for you? So the vision system developed here can be used as a ground truth in R&D and testing in a product design phase. And it can also be used as a standalone monitoring system as an alternative to the traditional vibration-based monitoring systems. Secondly, the direct image processing tool can be used as an objective support system in inspection of gearboxes in or after the operational phase. The improved indirect indicators, so based on accelerometers, encoders, torque, temperature, and so on, they can be used as an alternative to currently used vibration-based indicators. And finally, the gear degradation test setups and the corresponding datasets can be used for benchmarking and for validation of condition monitoring solutions. With that, I would like to thank you for listening to us, and we would be happy to answer your questions. Thank you.
Great. Thank you, Toby. Let's see if we have questions from anyone. I don't see any question in the chat. No questions at all. That's usually a very good sign. Well, okay, great. Thank you. Thank you everyone for joining us here. Thank you, Jordi and Toby, for this inspiring presentation. I will send a recap of this presentation or the video of the presentation to everyone here and subscribed later this week. And I see all kinds of thank yous coming in. Thank you for that. And I wish you all a very good day today. Goodbye.
I do see one question now.
Really?
Yes.
Oh, that's
Just
good
at the
that you
end.
saw that. Yes, okay. Is the detection system deployed online or is it currently working with offline data? Is the question.
So there's a two-part question. There's a two-part answer to this. I will answer for the direct data, and I will give for the indirect to you, Toby. That will be better. So right now, the vision-based side of it is still in situ. So it's data that's captured during the test and is processed afterwards. However, during the project, we did also work on a cloud platform to go with this, where the data is automatically uploaded to. And with some additional work, it would become possible to turn this into a more online system. The biggest question here is the deep learning models required for it. If the data sets are very similar to each other, it could potentially still work, but in a situation where the images look quite different from the ones we trained the model on, some more additional learning would be required. So if it's always the same setup, you could turn it into online, but for a new setup, they would always have to start offline.
And then for the indirect part, this detection is also online. So we capture our data, and at the same time, we analyze the data, we apply the indicators, and we can monitor the result over the timeline of the test. For the more advanced indicators, we typically post-process, so we process them after the tests, but the windowing strategy that we apply for the detection only uses data before, until this acquisition. It doesn't use data that still needs to come. So it can be directly deployed using the same cloud system for real-time fault detection.
Okay, great. Any more questions? No, I don't think there are any more questions. Okay, great. Well, thank you, everyone. Have a nice day. Goodbye, Jordi, Toby, and everyone else. Goodbye.
Thank you, everyone. Bye.